Good morning, everyone, and welcome to today's webinar, Delamination of Coating from a Ship's Hull. We're glad that you're joining us. My name is Josiah Lockley, and I'm with Paint Square. This webinar is organized by Paint Square and is part of our 2018 webinar series. To learn more, please visit www.paintsquare.com/webinars. Now, before we begin the main presentation, let's take a few moments to describe the format of today's webinar. The presentation from Robert Leggett of KTA Tater will be lecture style and last about 45 minutes. This will be followed by a 10-minute question and answer session. There you'll have the opportunity to submit questions via the questions chat box, which is part of your GoToWebinar control panel that you should see on the right-hand side of your screen. If you're having any technical issues, you may use that questions box to send questions of that nature, and we'll do the best we can to address them if anything comes up. The presentation slides are available for download at paintsquare.com/webinars. Look for the title of this webinar in the archive. We are also recording today's webinar, and we will make it available for replay in our archive at durabilityanddesign.com/webinars. Expect to see the recording uploaded to the site by around 5 p.m. Eastern Time today. It's my pleasure to introduce now our speaker today, Robert Leggett. Robert is the KTA Laboratory Services Manager and has more than 15 years experience in the protective coatings industry. He holds a PhD in Materials Science and Engineering from the University of Virginia. He joined KTA in August 2016 as the Laboratory Services Manager, overseeing the operations of the analytical and physical testing laboratories. In this position, he oversees all laboratory services, which include paint, corrosion, and material testing services, coating failure investigations, coatings research, and compositional analysis. Prior to joining KTA, he held various senior research and technical management positions with the United States Steel Corporation in Pittsburgh, Pennsylvania. At this point, I'm going to turn the presentation over to Rob.
All right, thank you, Josiah. Today we're going to be discussing the delamination of coating from a ship's hull. I'd like to point out before I begin that this investigation has been reported in the most recent issue of the JPCL and was authored by Cheryl Roberts. So this adhesion failure occurred on an aircraft carrier, and before we can really get into any of the details, we need to go over some terminology. The coating systems used on an aircraft carrier vary according to the anticipated exposure environment. For instance, the freeboard is the part of the hull that is above the immersion line. Similarly, the underwater hull is that portion of the hull we would expect to be continuously immersed. The boot top is the part of the hull that will have varying degrees of immersion depending on the loading in the boat. The light load line is where the ship should sit in water when it is unloaded. And the deep load line is the deepest that the ship can safely rest in the water until buoyancy becomes a concern. As a result of this varying immersion, the environment is going to be different. For example, in the underwater hull in the boot top, you would need an anti-corrosion layer as a primer, top coated with an anti-fouling layer. In contrast, in the freeboard, that area is going to be continually exposed to sunlight, and you would need a coating that has UV stability as the top coat. Right now, I'm going to go through the coating application sequence just so that everyone's on the same page as how this was applied. I would like to point out, for those of you that downloaded the preview presentation, that this is all consolidated into a single figure just for the ease of archival purposes. The first layer that was applied to the entire hull was a red epoxy anti-corrosion coating that had a polyamide and polyamidoamine hardener. A second layer was applied of the epoxy anti-corrosion coating that was gray. This is frequently done in a number of industries to use different colors so that the coating applicators or the coating inspectors can easily differentiate the different coating layers. A red anti-fouling coating composed of a polyamide cuprous oxide was applied to both the underwater hull and the top boot. This was followed by a black anti-fouling coating on the boot top and the underwater hull. A red anti-fouling coating was applied only in the underwater hull to differentiate the boot top from the underwater hull, and a second layer of the black anti-fouling coating was applied in the boot top. Finally, a polysiloxane coating was applied to the freeboard to give it the UV stability. So KTA was contacted to conduct the failure investigation, which was handled by Ken Tater. And the picture we see here shows a tugboat going out to an aircraft carrier. And the reason we show this is, one, to give you a sense of scale. You can see the people on the right of the image in the orange vest, give an idea of the scale of the aircraft carrier. Also, this was included to show that the only way to really access the failure site was via tugboat. The coating was observed to be peeling on the boot top, and this was occurring on both sides of the ship, primarily though on the port side. The images we see here are on the both sides of the ship, looking towards the rear of the aircraft or the aft. Similarly, peeling was also observed sporadically in the freeboard, and this was within a band above the deep load line that extended maybe a foot to a foot and a half. Samples were secured from several locations in order to look at the different types or coating systems that were involved. So for the upper area, this was an intact coating where there were no adhesion issues. This was taken in the freeboard well above the DLL. In the middle region, we're looking at areas where peeling had been observed, and it was in that band just above the DLL. Finally, in the lower area, we'd sampled an area of the boot top. These samples were mechanically chipped to bare metal, and what the red that you're seeing in these areas is actually a cohesive failure within the red anti-corrosion primer. It should be noted that lots of the samples were readily available by just removing them by hand because they had already started to peel. The laboratory investigation was designed to address two questions. One, why did the gray polysiloxane coating disbond in the freeboard just above the DLL? Secondly, why did the anti-fouling coating disbond from the anti-corrosion coating in the boot top? When we looked at the paint chips from the freeboard using an optical microscope, we found a difference between the areas where the paint was peeling in what we've referred to as the middle location versus the area where the coating was intact in the upper location. And what we found was the presence of a additional and unexpected red anti-fouling layer in between the gray polysiloxane and the gray anti-corrosion coating. And this suggested to us that the coating failure was the result of an inadvertent application of the red anti-fouling coating above the boot top. When we looked at samples of the paint chips that had peeled from both the boot top and the area just above the DLL, we saw a red coating on the backside. In order to confirm the identity of that coating, we used a simple MEK rub, which identified that coating as the red anti-fouling coating. We knew this because the red anti-fouling coating was known to be soluble in the MEK, whereas the red anti-corrosion coating, because it was an epoxy, was not going to be readily soluble in the MEK. The gray anti-corrosion layer, as I previously mentioned, was an epoxy, which was actually a two-part epoxy. And one issue that's frequently of concern is the mix ratio. So we used two different methods to analyze the mix ratio of the gray anti-corrosion layer. The first method we used was a nitrogen combustion method. So in this method, what you do is you take the paint chip and you put it in a furnace under oxidizing conditions, which produces nitrous oxide, various forms of nitrous oxide or nitrogen oxide species. This is then catalytically reacted over copper to produce elemental nitrogen, which can then be detected by infrared spectroscopy. When we compared properly mixed one-to-one control samples, we found that 5 out of the 7 samples that we investigated had excess nitrogen, which is indicative of excess hardener. And the mix ratio of the hardener to resin components ranged from 1.05 to 1 to as high as 2 to 1. These results were confirmed using infrared spectroscopy analysis. And in this method, we looked at different peaks in the infrared spectrum of a coating chip that would be attributable to either the hardener or the resin components. The peak that we see at 1506 wave number was attributed to the epoxy component, while the peak at 1454 wave number is attributable to hardener. And if by comparison of undercatalyzed versus overcatalyzed images that we show here, you can see that the relative band intensity changes as that mix ratio changes. This analysis indicated the presence of excess hardener in the gray anti-corrosion coating. A recoat study was undertaken, and in this we applied the gray anti-corrosion coating, allowed that to cure, and then we applied the at various time intervals we applied the red anti-fouling coating. What we found was that the adhesion was markedly better for recoat windows between the gray anti-corrosion coating of 2 hours versus longer times. This suggested to us that if there was an excessive amount of time in between application of the anti-fouling coating after application of the anti-corrosion coating, poor adhesion could be expected. The coating interval study was followed by a tack time test. And tack time is defined as the curing or drying period at which application of finger pressure on the coating results in only a slight impression without any removal of the coating on the finger, meaning it's basically the time in which the coating is no longer wet, but you can still see the effect of a slight finger pressure. We looked at two variables. We looked at the effect of the substrate, so we looked at both steel panels and glass panels. Similarly, we looked at different mix ratios. This was in the range of the control samples, which were a 1:1, and then we went as high as a 1.4 hardener to a 1 part of the resin component. What we found was that when you increased the when you increased the hardener component, the tack time went from 2.5 hours to something in the range of 1 to 1.5 hours. And this was seen in both the steel and the glass panels. This indicated to us that there was a narrow window at which the antifouling coating could be applied, which was exacerbated by the incorrect mix ratio. So in conclusion, we found that disbonding that occurred above the deep load line was a consequence of application of the polysiloxane over the antifouling coating instead of the anti-corrosion coating. We also found that there was off-ratio mixing of the gray epoxy anti-corrosion coating in some cases. Spontaneous disbonding and poor adhesion of the anti-fouling coating below the DLL was a result of exceeding the tack time of the anti-corrosion coating, which is aggravated by the off-ratio mixing. At the conclusion of the investigation, our recommendation to our client was for the shipyard and the coating contractor to review QA and QC records to determine in which areas the tack time was likely to have been exceeded. Furthermore, it was recommended that the coating should be removed in those areas where the peeling was observed or had been identified as being susceptible. It was recommended that the coating be removed either by hand or mechanical tool cleaning and or high pressure or ultra high pressure water blast cleaning. Oops.
Okay, thank you very much, Rob. Now at this point, we're going to open up the floor to questions. So if you'd like to submit a question, please enter it into the questions chat box located in the GoToWebinar control panel on the right-hand side of your screen. We'll select questions to read aloud for Rob to answer. Time restraints may prevent us from reading and responding to all questions in the session, but the submitted questions are logged and we'll do our best to follow up with responses in the weeks to come. So regarding some of these questions, right off the bat, we always get a handful of questions regarding where can I access the slides and can I access a recording of the webinar? And the answer to both those questions is absolutely. If you want to view a recording of the webinar or access the slides, just go to paintsquare.com/webinars. Click on the title of today's webinar. After you click on the title of today's webinar, you'll see a link that says presentation slides where you can access today's slides. As far as the recording, expect it to be ready by around 5 p.m. today at the very latest. The recording will be uploaded to the same place, paintsquare.com/webinars, again, just click on the title of the webinar today, and you will see a video of the webinar right at the top. So without further ado, I'm going to actually turn the microphone back over to Rob. He's in the studio with me, so he's going to read the questions over the air himself and answer them as well. So we'll be with you in just a moment.
All right, the first question that we received was, how did we collect the samples? It appears that the areas are very square. I guess to be honest, the images that we used for this presentation in the article were selected primarily to represent where the samples were chosen, and isn't necessarily representative of all sample areas. The samples were collected by marking off the area of interest and scraping with an air-driven chisel hammer while holding a plastic bag beneath it to collect the samples. And I think what the question is intended to ask is, was there any way that we were able to cut out a intact sample the size of the as depicted in the images that we've shown? And that was not the case. We just chiseled the pieces out. The second question we received is the tack time the same as the recoat window? And yes and no. In general, they are not the same thing. The tack time is specifically defined as the response of the coating as it cures. And the recoat window is the time that the coating manufacturer specifies for applying a second coating. In this specific case, the recoat window was defined as the tack time by the manufacturer. The third question is, why would the tack time affect adhesion? And I'll take a stab at that question. It's not really within the scope of our investigation, but typically when you're applying one coating on top of another, the solvents within the top coat need to be able to dissolve the immediate surface of the undercoat to allow diffusion of the two coatings in one another to establish that bond. And in this case, what likely happened is that when you exceeded the tack time, the undercoat was too fully cured in order for the solvents to sufficiently dissolve it and establish that bond. Looking at the other questions we've received, there are some questions about whether or not the polysiloxane was epoxy or acrylic based, and whether or not it was a mill DTL 24441 type primer. And I can't answer those at this time. I don't have that information in front of me, but I can follow up with the person that asked the question. There was a similar question on the whether or not the polysiloxane was an epoxy terminated. There is another question. Let me read this and see if I can rephrase it. One question is asking about that the failure on the ship appears to be a delamination of the coating, but that does not appear to be the same type of delamination that was shown in the adhesion test. The best way I can address that is the Delamination that you see when the coating is in its service environment is affected by a number of factors. It could be the wave action, it could be water penetration, while none of those can be accurately replicated in a lab. And when we did our testing, it was a simple tape test on top of either the X hatch or a cross hatch. So the physical manifestation of the delamination is most likely a result of limitations of laboratory testing. One of the questions that we received was whether or not the pot life of the mixed two-part epoxy coating would affect the adhesion, and it very well may, but that was not within the scope of the testing that we conducted. So that is, unless there are any other questions that anyone would like to submit. Okay, so yeah, we got one last question. This one was, what is the smallest sample size that you can use and still effectively run an IR analysis? And that is largely dependent on the type of microscope or spectrometer that you're using. In this case, we're using a spectrometer, and we carefully extracted a portion of the gray anti-corrosion coating from a chip that we sampled from the failure location and made a KBR pellet. And this can be a very small piece of material that's then ground up. So I can't really give you a size, except for that it's, you know, maybe the size of a, much less than a pencil tip or a pencil eraser. So that looks like that's all the questions that we've received. So I will follow up with the people that asked questions that had information that is not readily available at this moment. Thank you.
Okay, once again, I'd like to thank Rob for a great presentation. Before we finish today's webinar, there's some final topics I want to cover with you guys. First off, as I mentioned at the beginning of the webinar and during the Q&A, the presentation slides are currently available for download at paintsquare.com/webinars. Today's presentation has been recorded and will be uploaded by the end of the day today. For those of you not in different time zones, I should say, that would be around 5 p.m. Eastern Time. Sign up for the Paint Square News daily newsletter at paintsquare.com/PSN. You can find news, features, classified listings, quizzes, opportunities to interact online with your colleagues in the industrial coatings industry, and of course, webinars. Again, paintsquare.com/PSN. Finally, on behalf of Paint Square, I'd like to thank Rob of KTA Tater for a great presentation today, and of course, all of you for joining us. We look forward to presenting more webinars that will be educational and useful in your work. This concludes today's webinar. Have a great day, everyone.